The Mathematical Analysis of Logic, being an essay towards a calculus of deductive reasoning, by George Boole. Let us employ the symbol 1, or unity, to represent the universe, and let us understand it as comprehending every conceivable class of objects, whether actually existing or not, it being premised that the same individual may be found in more than one class, inasmuch as it may possess more than one quality in common with other individuals. Let us employ the letters uppercase X, uppercase Y, uppercase Z to represent the individual members of classes, uppercase X applying to every member of one class as members of that particular class, and uppercase Y to every member of another class as members of such class, and so on according to the received language of treatises on logic. Further, let us conceive of a class of symbols lowercase x, lowercase y, lowercase z possessed of the following character. The symbol lowercase x operating upon any subject comprehending individuals or classes shall be supposed to select from that subject all the uppercase x's which it contains. In like manner, the symbol lowercase y operating upon any subject shall be supposed to select from it all individuals of the class uppercase y which are comprised in it, and so on. When no subject is expressed, we shall suppose 1, the universe, to be the subject understood, so that we shall have x equals x, 1. The meaning of either term being the selection from the universe of all the uppercase x's which it contains, and the result of the operation being in common language the class uppercase x, i.e. the class of which each member is an uppercase x. From these premises it will follow that the product lowercase xy will represent in succession the selection of the class uppercase y, and the selection from the class uppercase y of such individuals of the class uppercase x as are contained in it, the result being the class whose members are both uppercase x's and uppercase y's. And in like manner the product lowercase x, y, z will represent a compound operation of which the successive elements are the selection of the class uppercase z, the selection from it of such individuals of the class uppercase y as are contained in it, and the selection from the result thus obtained of all the individuals of the class uppercase x which it contains, the final result being the class common to uppercase x, uppercase y, and uppercase z. From the nature of the operation which the symbols lowercase x, lowercase y, lowercase z are conceived to represent, we shall designate them as elective symbols. An expression in which they are involved will be called an elective function, and an equation of which the members are elective functions will be termed an elective equation. It will not be necessary that we should here enter into the analysis of that mental operation which we have represented by the elective symbol. It is not an act of abstraction according to the common acceptation of that term, because we never lose sight of the concrete, but it may probably be referred to an exercise of the faculties of comparison and attention. Our present concern is rather with the laws of combination and of succession, by which its results are governed, and of these it will suffice to notice the following. First, the result of an act of election is independent on the grouping or classification of the subject. Thus it is indifferent whether from a group of objects considered as a whole we select the class uppercase x, or whether we divide the group into two parts, select the uppercase x's from them separately, and then connect the results in one aggregate conception. We may express this law mathematically by the equation, all lowercase. Second, it is indifferent in what order two successive acts of election are performed. whether from the class of animals we select sheep, and from the sheep those which are horned, or whether from the class of animals we select the horned, and from these such as are sheep, the result is unaffected. In either case we arrive at the class horned sheep. The symbolical expression of this law is, all lowercase, xy equals yx. Third, the result of a given act of election performed twice, or any number of times in succession, is the result of the same act performed once. If from a group of objects we select the uppercase x's, we obtain a class of which all the members are uppercase x's. If we repeat the operation on this class, no further change will ensue. In selecting the uppercase x's, we take the whole. Thus we leave all lowercase xx equals x, or x squared equals x. And supposing the same operation to be n times thus performed, we have x to the nth power equals x, which is the mathematical expression of the law above stated. Footnote: the office of the elective symbol lowercase x is to select individuals comprehended in the class uppercase x. Let the class uppercase x be supposed to embrace the universe, then, whatever the class uppercase y may be, we have all lowercase xy equals y. The office which lowercase x performs is now equivalent to the symbol plus, in one at least of its interpretations, and the index law 3 gives plus to the nth power equals plus, which is the known property of that symbol. The laws we have established under the symbolical forms all lowercase x, open brackets, u plus v, close brackets, equals xu plus xv, 1, xy equals yx, 2, x to the nth power equals x, 3, are sufficient for the basis of a calculus. From the first of these it appears that elective symbols are distributive. From the second that they are commutative, properties which they possess in common with symbols of quantity, and in virtue of which all the processes of common algebra are applicable to the present system. The one and sufficient axiom involved in this application is that equivalent operations performed upon equivalent subjects produce equivalent results. Footnote: it is generally asserted by writers on logic that all reasoning ultimately depends on an application of the dictum of Aristotle, de omni et nullo. Whatever is predicated universally of any class of things may be predicated in like manner of anything comprehended in that class. But it is agreed that this dictum is not immediately applicable in all cases, and that in a majority of instances a certain previous process of reduction is necessary. What are the elements involved in that process of reduction? Clearly they are as much a part of general reasoning as the dictum itself. Another mode of considering the subject resolves all reasoning into an application of one or other of the following canons, viz. 1. If two terms agree with one and the same third, they agree with each other. 2. If one term agrees and another disagrees with one and the same third, these two disagree with each other. But the application of these canons depends on mental acts equivalent to those which are involved in the before-named process of reduction. We have to select individuals from classes, to convert propositions, etc., before we can avail ourselves of their guidance. Any account of the process of reasoning is insufficient which does not represent, as well as the laws of operation which the mind performs in that process, as the primary truths which it recognizes and applies. It is presumed that the laws in question are adequately represented by the fundamental equations of the present calculus. The proof of this will be found in its capability of expressing propositions and of exhibiting in the results of its processes every result that may be arrived at by ordinary reasoning. End of footnote. The third law, 3, we shall denominate the index law. It is peculiar to elective symbols and will be found of great importance in enabling us to reduce our results to forms meet for interpretation. From the circumstance that the processes of algebra may be applied to the present system, it is not to be inferred that the interpretation of an elective equation will be unaffected by such processes. The expression of a truth cannot be negatived by a legitimate operation, but it may be limited. The equation y equals z implies that the classes uppercase Y and uppercase Z are equivalent, member for member. Multiply it by a factor x and we have all lowercase xy equals xz, which expresses that the individuals which are common to the classes uppercase X and uppercase Y are also common to uppercase X and uppercase Z and vice versa. This is a perfectly legitimate inference, but the fact which it declares is a less general one than was asserted in the original proposition. Of expression and interpretation. A proposition is a sentence which either affirms or denies, as, all men are mortal, no creature is independent. A proposition has necessarily two terms, as men, mortal, the former of which, or the one spoken of, is called the subject, the latter, or that which is affirmed or denied of the subject, the predicate. These are connected together by the copula is, or is not, or by some other modification of the substantive verb. The substantive verb is the only verb recognized in logic. All others are resolvable by means of the verb to be, and a participle or adjective, e.g., the Romans conquered. The word conquered is both copula and predicate, being equivalent to were copula victorious, predicate. A proposition must either be affirmative or negative, and must be also either universal or particular. Thus we reckon in all 4 kinds of pure categorical propositions. First, universal affirmative, usually represented by uppercase A. Example, all uppercase X's are uppercase Y's. Second, universal negative, usually represented by uppercase E. Example, no uppercase X's are uppercase Y's. Third, particular affirmative, usually represented by I. Example, some uppercase X's are uppercase Y's. Fourth, particular negative, usually represented by uppercase O. Example, some uppercase X's are not uppercase Y's. Footnote. The above is taken with little variation from the treatises of Aldrich and Whatley. End of footnote. 1. To express the class not X, that is, the class including all individuals that are not uppercase X's. The class uppercase X and the class not X together make the universe. But the universe is 1, and the class X is determined by the symbol lowercase x. Therefore, the class not X will be determined by the symbol 1 minus lowercase x. Hence, the office of the symbol 1 minus lowercase x attached to a given subject will be to select from it all the not x's which it contains. And in like manner as the product xy expresses the entire class whose members are both uppercase x's and uppercase y's, the symbol y, open brackets, 1 minus x, close brackets, will represent the class whose members are uppercase y's but not uppercase x's, and the symbol open brackets 1 minus x, close brackets, open brackets 1 minus y, close brackets, the entire class whose members are neither x's nor y's. 2. To express the proposition, all uppercase x's are uppercase y's. As all the uppercase x's which exist are found in the class uppercase y, it is obvious that to select out of the universe all uppercase y's, and from these to select all uppercase x's, is the same as to select at once from the universe all uppercase x's. Hence, all lowercase xy equals x, or all lowercase x, open brackets, 1 minus y, close brackets, equals 0. 4. To express the proposition, some uppercase x's are uppercase y's. If some uppercase x's are uppercase y's, there are some terms common to the classes uppercase x and uppercase y. Let those terms constitute a separate class, uppercase v, to which there shall correspond a separate elective symbol, lowercase v. Then all lowercase v equals xy. And as lowercase v includes all terms common to the classes uppercase x and uppercase y, we can indifferently interpret it as some uppercase x's or some uppercase y's. 5. To express the proposition, some uppercase x's are not uppercase y's. In the last equation, write 1 minus lowercase y for lowercase y, and we have all lowercase v equals x, open brackets, 1 minus y, close brackets. The interpretation of lowercase v being indifferently some uppercase x's or some not uppercase y's. The above equations involve the complete theory of categorical propositions, and so far as respects the employment of analysis for the deduction of logical inferences, nothing more can be desired. But it may be satisfactory to notice some particular forms deducible from the third and fourth equations, and susceptible of similar application. If we multiply the equation 6 by lowercase x, we have all lowercase vx equals x squared y equals xy by 3. Comparing with 6, we find all lowercase v equals vx, or v, open brackets, 1 minus x, close brackets, equals 0, 8. And multiplying 6 by lowercase y and reducing in a similar manner, we have all lowercase v equals vy, or all lowercase v, open brackets, 1 minus y, close brackets, equals 0, 9. Comparing 8 and 9, all lowercase vx equals vy equals v, 10. And further comparing 8 and 9 with 4, we have as the equivalent of this system of equations the propositions: all uppercase v's are uppercase x's, all uppercase v's are uppercase y's. The system 10 might be used to replace 6, or the single equation, all lowercase vx equals vy, 11, might be used, assigning to vx the interpretation some uppercase x's, and to lowercase vy the interpretation some uppercase y's. But it will be observed that this system does not express quite so much as the single equation 6 from which it is derived. Both indeed express the proposition some uppercase x's are uppercase y's, but the system 10 does not imply that the class uppercase v includes all the terms that are common to uppercase x and uppercase y. In like manner, from the equation 7, which expresses the proposition some uppercase x's are not uppercase y's, we may deduce the system, all lowercase, Vx equals V, open brackets, 1 minus y, close brackets, equals V12, in which the interpretation of V, open brackets, 1 minus y, close brackets, is sum not uppercase y's. Since in this case Vy equals 0, we must of course be careful not to interpret Vy as sum uppercase y's. If we multiply the first equation of the system 12, viz. all lowercase, Vx equals V, open brackets, 1 minus y, close brackets, by y we have all lowercase, Vxy equals Vy, open brackets, 1 minus y, close brackets. Therefore, Vxy equals 0, 13, which is a form that will occasionally present itself. It is not necessary to revert to the primitive equation in order to interpret this, for the condition that lowercase Vx represents some uppercase x's shews us by virtue of 5 that its import will be some uppercase x's are not uppercase y's, the subject comprising all the uppercase x's that are found in the class uppercase V. Universally in these cases, difference of form implies a difference of interpretation with respect to the auxiliary symbol lowercase v, and each form is interpretable by itself. Further, these differences do not introduce into the calculus a needless perplexity. It will hereafter be seen that they give a precision and a definiteness to its conclusions which could not otherwise be secured. Finally, we may remark that all the equations by which particular truths are expressed are deducible from any one general equation, expressing any one general proposition from which those particular propositions are necessary deductions. This has been partially shewn already, but it is much more fully exemplified in the following scheme. The general equation, all lowercase, x equals y, implies that the classes uppercase x and uppercase y are equivalent, member for member, that every individual belonging to the one belongs to the other also. Multiply the equation by x and we have x squared equals xy, therefore x equals xy, which implies by 4 that all uppercase x's are uppercase y's. Multiply the same equation by lowercase y and we have, in like manner, all lowercase y equals xy, the import of which is that all uppercase y's are uppercase x's. Take either of these equations, the latter for instance, and writing it under the form all lowercase, open brackets 1 minus x, close brackets, y equals 0, we may regard it as an equation in which lowercase y, an unknown quantity, is sought to be expressed in terms of lowercase x. Now it will be shown that when we come to treat of the solution of elective equations, and the results may here be verified by substitution, that the most general solution of this equation is all lowercase y equals vx, which implies that all uppercase y's are uppercase x's, and that some uppercase x's are uppercase y's. Multiply by x and we have all lowercase vy equals vx, which indifferently implies that some uppercase y's are uppercase x's and some uppercase x's are uppercase y's, being the particular form at which we before arrived. For convenience of reference, the above and some other results have been classified in the annexed table, the first column of which contains propositions, the second equations, and the third the conditions of final interpretation. It is to be observed that the auxiliary equations which are given in this column are not independent. They are implied either in the equations of the second column or in the condition for the interpretation of V. But it has been thought better to write them separately for greater ease and convenience. And it is further to be borne in mind that although three different forms are given for the expression of each of the particular propositions, everything is really included in the first form. Table. The class uppercase X, lowercase x. The class not uppercase X, 1 minus lowercase x. All uppercase x's are uppercase y's. All uppercase y's are uppercase x's. X equals y. All uppercase x's are uppercase y's. Lowercase x, open brackets, 1 minus y, close brackets, equals 0. No uppercase x's are uppercase y's. Lowercase xy equals 0. All uppercase y's are uppercase x's. Some uppercase x's are uppercase y's. Lowercase y equals vx. Lowercase vx equals some uppercase x's. Lowercase v, open brackets, 1 minus x, close brackets, equals 0. Some uppercase x's are uppercase y's. Lowercase v equals xy, or lowercase vx equals vy, or lowercase vx, open brackets, 1 minus y, close brackets, equals 0. V equals some uppercase x's or some uppercase y's. Lowercase vx equals some uppercase x's. Vy equals some uppercase y's. Lowercase v, open brackets, 1 minus x, close brackets, equals 0. V, open brackets, 1 minus y, close brackets, equals 0. Some uppercase x's are not uppercase y's. Lowercase v equals x, open brackets, 1 minus y, close brackets. Lowercase v equals some uppercase x's or some not uppercase y's, or lowercase vx equals v, open brackets, 1 minus y, close brackets. Lowercase vx equals some uppercase x's. Lowercase v, open brackets, 1 minus y, close brackets, equals some not uppercase y's, or lowercase vxy equals 0. Lowercase v, open brackets, 1 minus x, equals 0. Vy equals 0. Of the conversion of propositions. A proposition is said to be converted when its terms are transposed. When nothing more is done, this is called simple conversion. E.g., no virtuous man is a tyrant is converted into no tyrant is a virtuous man. Logicians also recognize conversion per accident or by limitation. E.g., all birds are animals is converted into some animals are birds. And conversion by contraposition or negation as every poet is a man of genius converted into he who is not a man of genius is not a poet. In one of these three ways, every proposition may be iteratively converted, viz. I and E simply A and O by negation, A and E by limitation. The primary canonical forms already determined for the expression of propositions are all uppercase x's are uppercase y's. Lowercase x, open brackets, 1 minus y, close brackets, equals 0. A. No uppercase x's are uppercase y's. Lowercase xy equals 0. E. Some uppercase x's are uppercase y's. Lowercase v equals xy. I. Some uppercase x's are not uppercase y's. Lowercase d equals x, open brackets, 1 minus y, close brackets. O. On examining these, we perceive that E and I are symmetrical with respect to lowercase x and lowercase y, so that lowercase x being changed into lowercase y and lowercase y into lowercase x, to the equations remain unchanged. Hence, E and I may be interpreted into no uppercase y's are uppercase x's, some uppercase y's are uppercase x's, respectively. Just we have the known rule of the logicians that particular affirmative and universal negative propositions admit of simple conversion. The equations A and O may be written in the form, all lowercase, open brackets, 1 minus y, close brackets, open curly brackets, 1 minus open brackets, 1 minus x, close brackets, close curly brackets, equals 0. V equals, open brackets, 1 minus y, close brackets, open curly brackets, 1 minus open brackets, 1 minus x, close brackets, close curly brackets. Now these are precisely the forms which we should have obtained if we had in those equations changed lowercase x into 1 minus lowercase y, and y into 1 minus lowercase x, which would have represented the changing in the original propositions of the uppercase x's into not uppercase y's, and the uppercase y's into not uppercase x's, the resulting propositions being all not y's are not x's, some not y's are not x's, A. Or we may, by simply inverting the order of the factors in the second number of O, and writing it in the form all lowercase v equals open brackets 1 minus y close brackets x, interpret it by I into some not uppercase y's are uppercase x's, which is really another form of A. Hence follows the rule that universal affirmation and particular negative propositions admit of negative conversion, or, as it is also termed, conversion by contraposition. The equations A and E, written in the form all lowercase open brackets 1 minus y close brackets x equals 0, yx equals 0, give on solution the respective forms all lowercase x equals vy, x equals v open brackets 1 minus y close brackets, the correctness of which may be seen by substituting these values of x in the equations to which they belong, and observing that those equations are satisfied quite independently of the nature of the symbol v. The first solution may be interpreted into some uppercase y's are uppercase x's, and the second into some not uppercase y's are uppercase x's, from which it appears that universal affirmative and universal negative propositions are convertible by limitation, or, as it has been termed, per accidens. The above are the laws of conversion recognized by A.D.P. Whatley. Writers differ, however, as to the admissibility of negative conversion. The question depends on whether we will consent to use such terms as not uppercase x and not uppercase y. Agreeing with those who think that such terms ought to be admitted, even although they change the kind of the proposition, I am constrained to observe that the present classification of them is faulty and defective. Thus the conversion of no uppercase x's are uppercase y's into all uppercase y's are not uppercase x's, though perfectly legitimate, is not recognized in the above scheme. It may therefore be proper to examine the subject somewhat more fully. Should we endeavour, from the system of equations we have obtained, to deduce the laws not only of the conversion but also of the general transformation of propositions, we should be led to recognize the following distinct elements, each connected with a distinct mathematical process. First, the negation of a term, i.e. the changing of uppercase x into not uppercase x, or not uppercase x into uppercase x. Second, the translation of a proposition from one kind to another, as if we should change all uppercase x's are uppercase y's into some uppercase x's are uppercase y's, A into I, which would be lawful, or all uppercase x's are uppercase y's into no uppercase x's are uppercase y's, A into E, which would be unlawful. Third, the simple conversion of a proposition. used conversions by which propositions are expressed. We have all uppercase x's are uppercase y's, all lowercase x, open brackets, 1 minus y, close brackets, equals 0. A. No uppercase x's are uppercase y's, lowercase xy equals 0. E. Write C in the form all lowercase x, open curly brackets, 1 minus open brackets, 1 minus y, close brackets, close curly brackets, equals 0. And it is interpretable by A into all uppercase x's are not uppercase y's, so that we may change no uppercase x's are uppercase y's into all uppercase x's are not uppercase y's. In like manner, A interpreted by E gives no uppercase x's are not uppercase y's, so that we may change all uppercase x's are uppercase y's into no uppercase x's are not uppercase y's. From these cases we have the following rules. A universal affirmative proposition is convertible into a universal negative, and vice versa by negation of the predicate. Again we have some uppercase x's are uppercase y's, or lowercase v equals xy. Some uppercase x's are not uppercase y's, or lowercase v equals x, open brackets, 1 minus y, close brackets. These occasions only differ from those last considered by the presence of the term lowercase v. The same reasoning therefore applies, and we have the rule. A particular affirmative proposition is converted into a particular negative and vice versa by negation of the predicate. Assuming the universal proposition, all uppercase x's are uppercase y, or lowercase x, open brackets, 1 minus y, close brackets, equals 0. No uppercase x's are uppercase y, or lowercase xy equals 0. Multiplying by x we find all lowercase vx, open brackets, 1 minus y, close brackets, equals 0, vxy equals 0, which are interpretable into some uppercase x's are uppercase y, I, some uppercase x's are not uppercase y, O. Hence a universal affirmative is convertible into a particular affirmative, and a universal negative into a particular negative without negation of subject or predicate. Combining the above with the already proved rule of simple conversion, we arrive at the following system of independent laws of transformation. First, an affirmative proposition may be changed into its corresponding negative, A into E or I into O, and vice versa by negation of the predicate. Second, a universal proposition may be changed into its corresponding particular proposition, A into I or E into O. Third, in a particular affirmative or universal negative proposition, the terms may be mutually converted. Wherein negation of a term is the changing of uppercase x into not uppercase x, and vice versa, and is not to be understood as affecting the kind of the proposition. Every lawful transformation is reducible to the above rules. Thus we have all uppercases are uppercase y's, no uppercase x's are not uppercase y's, vice versa, no not uppercase y's are x's, by third rule, all not uppercase y's are not uppercase x's by first rule, which is an example of negative conversion. Again, no uppercase x's are uppercase y's, no uppercase y's are uppercase x's, third rule, all uppercase y's are not uppercase